So here's a couple more sets that we could look at, and maybe write these in roster form, and then look at a couple other interesting aspects here. So the first one, set A, this one's just kind of weird to read through, but if we follow through carefully, it might make some sense. First of all, set A is all of the x's such that n, now look, I switched variables, but that's intentional. N is in the natural numbers, n is less than or equal to 4, and x is equal to 2n. So if you think about that, you've got natural numbers, n is a natural number, n is less than or equal to 4, but n is not in the set, x is. So how do I find x? Well, I take I take n and double it. So I take all of the n's in the natural numbers that are less than or equal to 4 and double them to find x, okay? So, to figure out the roster notation, I just figure out what the n values are. I have n equal to 1, 2, 3, and 4, right? They're natural numbers less than or equal to 4. And then I double them. So that means the x values are going to be 2 times 1, which is 2, 2 times 2, which is 4, 2 times 3, which is 6, and 2 times 4, which is 8. Oops, didn't write that well. Right? So I get the numbers 2, 4, 6, 8. Those are the even numbers, less than 10, basically. And so, well, not included, even natural numbers, I should say, not including 0. And so A is the set 2, 4, 6, 8. All right. So again, you're using information about a variable to find values of another variable. All right. So you're using information about n to find x, and x is the actual elements of the set. X are the elements of the set. Okay. Now let's look at B. B, these are all values of y, such that y is a suit in a deck of cards. Well, there are 4 suits in a deck of cards, right? There's spades, clubs, hearts, and diamonds. And so the set B contains spade, heart, or no, spade, club, doesn't matter the order really. Heart. Oops. My artistic abilities are failing me here. And diamond. Okay. Put a comma in between each of those. And so these are the 4 numbers in set A, the 4 suits in set B. Now, what's interesting is that these sets are very unrelated in terms of what their actual elements are, but they're related in their cardinalities. Notice that n of A is equal to 4, and n of B is equal to 4. The cardinality of A, the cardinality of B, the number of elements in each one is 4, which makes these 2 sets equivalent, even though they're not equal. Okay, so we'd say that A and B are equivalent because n of A equals n of B. All right? Now, what's interesting is that when you have 2 sets that are equivalent, not equal, but equivalent, you can correspond the elements of one set directly to another. In other words, I could just relate the number 2 to spade, 4 to club, 6 to heart, and 8 to diamond. And so we have what we call a one-to-one correspondence. A correspondence is just a relationship where you link them together, and one-to-one means there's one from each set linked together, okay? So there's one from set A matched with one from set B. So it's a one-to-one correspondence. A one-to-one correspondence occurs when two sets are equivalent. In other words, their cardinalities are the same. Okay? So they can be placed in a one-to-one correspondence, the elements of each set. This is an interesting idea, and sometimes that correspondence can be represented mathematically. If I took another set, maybe I just take the set C, I'll make one up here. It's one that we've kind of already looked at with the n values. 1, 2, 3, 4. Okay. It's the values of n that I use to calculate set A. Then the correspondence between C and A, right, so correspondence took 1 and made it 2, took 2 and made it 4, took 3 and made it 6, 4 and made it 8. That one-to-one correspondence can be actually represented mathematically as an equation x equals 2n. So this actually is a one-to-one correspondence between the sets, the set containing these n values and the set containing these x values. It's kind of interesting. Okay, so sometimes the correspondence is mathematical in nature. Sometimes it's just a labeling, a pairing up of the elements. Okay, and so one-to-one correspondences exist when two sets are equivalent. By the way, this is ENCE, not ANCE. There we go. All right. Now, what's interesting is that there are some very, very large sets. In fact, there are some sets that are infinite in size, like the set of all natural numbers, the set of all even numbers, odd numbers, those sorts of things. And so we're going to take a look at those for a moment and look at their cardinalities. So let's say we had a set. I'll call it, well, of course, let's do the natural numbers. Right? I don't even need to define it because we know the natural numbers. Now, I will actually write the roster form just to have it up here. Well, the cardinality of the natural numbers, you would think is infinite, right? Or in infinite value, but infinity is not a number. It doesn't really make sense as a number. It's an idea of sort of a never-ending, it's sort of a goal that you want to get to, but you never can. But it's not actually a number, okay? And so the set of natural numbers does still have a cardinality, right? We say that n is infinite in size, but we don't use infinity as a cardinal number. That wouldn't make much sense. Instead, we're going to use a symbol. It's a Hebrew symbol called Aleph, or Aleph. I don't know exactly how to say it. It is kind of a strange looking symbol, actually. I don't write it very often, and so it's not really familiar. It kind of looks like an N with squigglies on the ends instead of straight lines. And so this Aleph is kind of like an infinite, but it's a specific kind of infinity. And we call this actually Aleph not, or Aleph null. It's a subscript of 0 next to it. It's the first in its size. Lots of sets have this size, Aleph not. The set of even numbers has the exact same size. If I had, let's say I put set, I'll call it E. Set E is the set of all x values such that x is in n. How do I do that? Oh, it would be similar to this, wouldn't it? x such that n is a natural number and x is equal to 2n. Right, that'd be the set of all even numbers. In fact, I could list them all off. Instead of 1, 2, 3, 4, and so on, it's actually the set 2, 4, 6, 8, and so on. But there is a one-to-one correspondence here. So what's interesting is that 1 pairs up with 2, 2 pairs up with 4, 3 pairs up with 6, 4 pairs up with 8, 5 pairs up with 10, 6 pairs up with 12, and so on. And you can create a one-to-one correspondence. In fact, it's exactly this same correspondence. And so even though these are both infinite in size, the cardinality of both of them, the natural numbers and the set of evens, is the same. It's both this Aleph naught. Okay? And so what we have here are two interesting sets. What's interesting about it is that E contains, or all of the elements of E are also in N, but notice it's missing an infinite number of them, right? So it's missing all the odds. If I took N, pull out every odd number, which is an infinite set, I get the exact same size set, because I can still correspond one-to-one every element of both sets. That's fascinating. So you pull out an infinite number of elements, you get the exact same size. And so that size is called Aleph naught. In fact, the odd numbers, the odd natural numbers, have the same cardinality as both of these. As do many other sets have this same size. What we're going to find in the next section is that there are other sizes of infinity based upon other types of sets that are larger than this infinite set. Okay, and so we have finite sets which have a finite number as their cardinality, and infinite sets that have these alephs as their cardinality. They're infinite in size, but some are still larger than others, which is weird. I get that, and so we're going to talk about that in the next section. It's kind of a nice segue as we move forward.